Okay, good evening. Welcome to the last live stream for this semester. If you've got some ideas for the fall semester, I'm going to be moving to Washington, D.C., setting up a new studio and everything. So looking forward to maybe doing some different content in the fall. Just wrapped up a really great, what I think is a really great course in navigation problems near coastal and oceans. So there's a link in the video description down below if you wanted to check that out. But also I'll just take a quick pop over there and show you what I'm talking about before we get started tonight. We've got a few esoteric problems tonight. We're going to do some random stuff tonight. So here's that course if you want. There's a link in the video description below. If you use the code NEWCOURSE, you'll get 50% off. And then for some of you that have been here every week, if you want to email me, I got another course code for you guys as well. But navigation problems for Coast Guard exams, it's like 35 hours long. Dozens of problems to go along with the theme for the chart plotting for Coast Guard exams and the rules of the road for Coast Guard exams as well. And then I got the free courses there as well for the fundamentals of the maneuvering board, celestial navigation basics for mariners, and then some of these navigation general questions. So if you've enjoyed the content over these past 13 weeks or so, if you don't mind at least checking that out and maybe passing the word along to a friend or something, I would be eternally grateful for you there. All right, so for tonight, we are going to do, I thought of 3 fun problems that are kind of just random ones out of the Coast Guard database. And the first one is going to be a currents problem. And so we haven't really done tides and currents yet during these live streams, but there are a whole bunch of them in that navigation general course that's free on the website. So if you want to check out like the basics of tides and currents, you can do that. Generally though, the currents and the tide problems are like, what is the state of the tide at 13:30 on this particular day? Or what is the state of the current on at 14:17 on this day, kind of thing. And so those are like your basic tide current problems that we all solve. The one we're going to solve tonight is tricky. It's what is the period of slack water in Cape Cod Canal? How long is it going to last? Then we're going to solve one about planets on the Starfinder. That was a request from a couple weeks ago when we did the Starfinder problems. We didn't do any planet problems, so we'll do one of those tonight. And then finally, we'll do an amplitude of the moon when it's not in the right place with like all kinds of corrections and stuff. So just 3 kind of random questions that I thought might be fun to go through and illustrate a few concepts. All right, so if you go into the video description block down below and hit more, you should be able to see the problems that we're going to do tonight with the answers. Don't peek at those if you don't want. But the first problem is a current problem. So let me just grab my problem here, and it reads, you will transit the Cape Cod Canal on 7 November 1983. All the current and tide problems are from 1983 in the database, just because it's so long ago, none of us were alive yet, right? Just kidding. But they're all from the same year, so they don't have to change the problems every year. And we want to be there at 16:55 Eastern Standard Time, which is zone descriptor +5. So no daylight savings time, no kind of weird stuff going on there. What is the period of time that you'll have slack of about 0.5 knots? How long will that be? And if you've ever transited the Cape Cod Canal, holy cow, it's not slack very much at all, and it really rips through there. What makes this problem tricky is, like I said earlier, it's not kind of your basic current problem. It's not asking what is the state of the current at 16:55. It's saying how much slack time are you going to have. So for this, we're going to need the tidal current tables. So I'm holding one. You're probably not, but I'll take you along on a journey here with the camera and show you kind of what's going on. Now, normally for tidal current problems, I really recommend you do a structure like this. Up here is going to be all your offsets. And over here is going to be your reference station. So let's say your reference station was like Boston, and you were solving a current problem for Gloucester, Massachusetts, which is a small fishing town just northeast of Boston there. You would find it for the big town reference station. You would find some offsets. So say the slack time was like 12:30 here. And the offset for Gloucester is like plus 10 minutes. Well, the slack time for Gloucester then is going to be 12:40. And then in this block, you can just kind of answer whatever question they throw at you, right? That's your normal tide, your normal current strategy. Well, this problem is different, and what makes it tricky is a couple things that we'll show you as we go along. First things first, let's take a look at the tidal current tables. So we're going to pop over to that, if I can work my camera correctly. And you should be looking at the tidal current tables now. This is Merchant Mariner Deck Material Part 2. Normally what we do for our first step is go into the back of the book, into the index, and find what we're looking for, Cape Cod Canal. All right, so I'm just gonna zoom in, don't get seasick or anything there. And here's the Cape Cod Canal Railroad Bridge. So it's station number 1781. Good to know. So our next step is then to go find station number 1781 in the back here. And this is going to be all the offsets for the Cape Cod Canal Railroad Bridge. What makes this problem unique, here is station 1781, Cape Cod Canal. There's no offsets. This is a daily prediction site. So all we have to do is go to on the Cape and we can find that stuff. So in one sense, they are saving us a little bit of time here when we go to find these corrections. So in that like grid structure, there's no offsets. So we're gonna have a little bit of an easier time, believe it or not. The Coast Guard's trying to make things easy for you. So I'll save you the agony of me watching me flip the page in the camera here. But we'll take a look at the Cape Cod Canal Railroad Bridge. And our date was 7 November. Okay, we'll pop back over to the book now. And so we've got the Cape Cod Canal. Flood is the F, ebb is the E. We're in November. And the way these are written, it gives a slack water time and then a maximum time. So floods and ebbs are maximum. Flood is an F, E is an ebb. Hard to see in the camera, I know. But down here on the 7th of November, we want to take our ship in at 16:55, and that just so happens to be exactly the slack time. Right before it, there's an ebb 13:45 of 4.8 knots. And there's a flood current afterwards at 20:01 of 4.6 knots. So that's the information that we need to get out of the tidal current tables, and I'll just go ahead and kind of reproduce that all up here. We had what was it, an ebb, and that was at 13:45, and it was 4.8 knots. I just pulled that out of the tidal current tables. No mystery there. The slack, and the time for slack was 16:55. How fast is the current going at slack? 0. That's the definition of slack. And then there's a flood, and the time for the flood was 20:01, a space odyssey, and the speed was 4.6 knots. You can see in the Cape Cod Canal that this current reverses itself quite significantly, right? And the period of time that we have going on is our main question. Is at 16:55, how much time? There's another TIE fighter for you there, Kylo Ren's TIE fighter. How much time is it going to be less than 0.5 knots? Is it going to be instantaneous? Is it going to be an hour? That's the big question. If we're going to take on canal, there's a great YouTube channel called Tim B at Sea. He's like a tugboat driver, and he takes his ship through the Cape Cod Canal from time to time. So check that out if you want, and you can see just how scary it is. Quick sea story for you. There I was. I won't say the expletive part that begins all sea stories. It was on a Coast Guard cutter. It was this one, actually. And we were going through the Cape Cod Canal. It was like 2 in the morning. We had to get back to Maine. And all of a sudden, our chart plotter went out. Like, okay, no worries. We're professional navigators. Then our radar went out. And then it was the fog came in. So it was really eerie going through the Cape Cod Canal. It's a tricky waterway. So that's not a place that you want to have that happen to you. Okay, back to the question. So what we want to do is we're going to use what's called Table 4 in the current tables to figure out the period of slack water. And in order to use Table 4, let's take a look at it, and that'll help us determine what we need to do. So here's table 4, the duration of slack water. Duration of slack water. So if you kind of read the instructions, I'll summarize them for you here, is table B should be used for crazy places. So table B says, what is the period with a velocity not more than, and then here's 0.5 knots and 0.4, etc. And what is the maximum current? So those are our 2 entry points, and we're going to come up with some kind of time out of it. So this actually looks pretty straightforward. The reason I marked it as a tricky problem is this is a daily predictions site, and the period of slack water is not a question that you see that often. I've never seen it on any of my exams. It is in the database, so we're prepared for it. But you never know when you're going to see something like that on an exam. So it's good to know. Okay, so what we need is the maximum current. Well, a maximum, and here's a maximum. So which one do we use? Well, we use the average. So the average max is going to be 4.7 knots. So really, that's going to be our entry point into the table. So let's pop back over to the table, and we'll take a look at what our result is. So if we have a maximum current of 4.7 knots, we're going to end up between the 4 and the 5. And we want a period of less than 0.5 knots. So we're going to end up sometime between the 17 and the 13 minutes. So I think this is something that we can definitely mentally interpolate. You know, we're 4.7, so we're 3/4 of the way from 4 to 5. So we should go 3/4 of the way from 17 to 13. And that's going to give us an answer of 14 minutes. 14 minutes. So that's the period of slack, which is less than half a knot, 14 minutes. So what we do is we take 1655, we add 7 minutes on that side, and we subtract 7 minutes on this side, and we can get the period of slack water. Right, and so if I do my math right, that's going to get us to 1702 for that end, and 1648 for this one. So the period of time when the current is less than half a knot is going to be from 1648 to 1702. So you can't get through the Cape Cod Canal in that amount of time, at least if you're following the speed limit of 10 knots. They're going to yell at you if you go faster, trust me. But that's the answer to the question. So kind of a very weird current question that often, but I thought it might be fun to go through. All right, so our next one is going to be a star finder problem. A star finder problem. So if you remember back a few weeks ago, we talked about starfinder problems. And the deal with starfinder problems is that we need to get the LHA of Aries if we want to use it. And here's a starfinder. So it's the white plate with the clear plates all over it. We got to figure all that stuff out. But let's set up our problem, talk a little bit of theory, and then we'll solve it there. Okay, so the Starfinder problem states that it's 2 February 1981. All the problems for celestial are in 1981. And at 0400, our zone time position was 2414 north and 163.28 west. We're on a course and a speed that's not actually required to answer the question, so I'll save you the effort there. And which of the following groups of stars or planets is best suited for a fix? So 2 quick theory things first. If you're out there on your boat floating along, you want to shoot objects that are like at least 25 degrees above the horizon and preferably less than 70 degrees up. This is a good viewing angle to shoot stars at, right? So that's going to be a good one. You know, that's going to be too high, that's going to be too low when we go to select these. And then if we flip this around, now we're on our boat and we're looking from the top down. You want those stars spread out throughout the sky so they make a good fix for you, right? You want a star over here and like another one over here and maybe another one over here. That would be good. If you had 2 stars that are right next to each other or 2 stars that are opposite from each other, they're not going to give you a fix. So that's what we're looking for when we have to select our stars. The second piece of theory is how do we set up the star finder? that's going to be based on the LHA of Aries. So if we're in the north up here, Aries is the point in the constellation Aries that is over London on the spring equinox. So it's kind of like the Greenwich of the sky. All right, and so if this is our longitude, and Aries has some longitude as well, it's called its Greenwich hour angle. Like maybe Aries is over here right now, that's going to be GHA. Then the difference is LHA, local hour angle. And that's what we have to get in order to use the Starfinder. So the name of the game is going to be to look up the GHA of Aries, figure out our longitude, and then GHA minus longitude equals LHA, at least in the Western Hemisphere, which is what this problem is going for. All right, enough theory. Let's get to the problem then. So if you look at the answers, they're kind of cool. There's Jupiter and Saturn in there, so we got to kind of figure out how to do all that stuff. And it's not a very long problem, believe it or not. It's just you got to manage some information. So we're going to need the Starfinder and the Nautical Almanac for this. So I'm going to open the Nautical Almanac to the day in question, the 2nd of February, before we come back to the whiteboard. Okay, so we've got that. Our first step in this problem is going to be to figure out what zone time we're actually observing on our watches, because we need to put all this into Greenwich Mean Time. So if we take our longitude, and this is almost always the first step in a celestial problem, take our longitude, 163, divide it by 15 degrees per time zone, gets you a time zone of plus 11 zone descriptor. If we add 11 hours to our zone time, that gets us to 1500 GMT. So that's the time that we're going to want to use. If we used 1100 or 400, we're not going to be right. All right, so that's good to know. The other thing we need to know is the GHA of Aries for this problem. So let's go take a look at that in the Nautical Almanac. So here's Aries over here, and we're on the 2nd of February at 1500. So it's going to tell us that the GHA of Aries is 357, 42.8. 357, 42.8. Right? While we're in the Nautical Almanac, there's some other information that we can write down. Right? Here's Venus, Mars, Jupiter, Saturn. Here's all the navigational stars. Down here is a critical piece of information. The SHA, or the sidereal hour angle of the planets, is listed right there. So we're going to want to note the sidereal hour angle of Jupiter, 169, and Saturn, 170. And that's actually interesting because it looks like they're right on top of each other. We also need to note the declination of those planets. So at 1500, the declination of Jupiter looks to be south 2 degrees, 43.7. Saturn is south 1 degree, 29.5. 1 degree, 29.5. Okay, so we noted all that information. I know it's challenging not having the Nautical Almanac maybe in front of you when you're looking at this, but if you can get the electronic version or get your hands on a copy, it's helpful. Looking up things like this is a skill for sure in the naughtiest of almanacs. So we said the GHA of Aries, we looked that up in the Nautical Almanac, and it was 342.8. And then our longitude over here was 163 degrees 28.0 west. So we have to subtract it to get LHA. Remember, LHA is GHA minus longitude. All right, so that's worth the calculator for sure. All right, 194. It's going to be critical information to setting up the Starfinder. We're definitely going to need that. However, we also need to look at the Starfinder and see where those planets are. They're not on there. We have to plot them on there directly. So let me clean up the board. I'll write down the information that we noted for the planets earlier. For Jupiter and for Saturn, the sidereal hour angle, which is really just like what you add to the Greenwich hour angle of Aries in order to find it in the sky, because it's just an offset. So it's related to the longitude of the planet, is 169 degrees, 57.7. The sidereal hour angle of Saturn was 170 degrees, 10.4. And we noted that the declination, I'll just write it here in a different color right below it, was south 2 degrees, 43.7, and south 1 degree, 29.5. All right, we'll come back to that in just a minute, but before we move on to the star finder, I wanted to just write all that stuff down. Okay, let's take a look at the star finder. I think we're done with the Nautical Almanac. Blah. All right, here is the star finder, and what it comes with is these transparent plates, right? So they have different latitudes on them. Spoiler alert, for Coast Guard problems, it's always going to be the 25 latitude, so that's good. We'll get rid of these. It comes with the base plate. Dropping a sick baseline there. The north side and the south side, all the stars plotted out there. We're going to be in the northern hemisphere. And it also comes with this red plotting plate, right? So for planets, we need to use this red plotting plate. It's got north latitude and south latitude as well. And so really what we're going to do is we're going to plop that on to the base plate, and then we can spin it to a certain part, and right here, and draw the planet in the correct place for the time of year. Right? So we have to do a couple of calculations in order to do that. Really just one calculation, and that is to calculate the rotation of the planet. Right ascension is another, astronomical term in essence for the longitude of the planet. It's all about kind of the longitude-based angles that we're dealing with, right? And so right ascension is just 360 minus the sidereal hour angle. So 360 minus this gives you your right ascension. Right, so 60 minus 57.7, 02.3, and then 359. So 190 degrees, 02.3, is the right ascension of Jupiter. 360 minus this will give us the right ascension of Saturn. (189.49.6) for the right ascension of Saturn. We need the declinations as well, and we can plot these things. And it's really actually pretty cool in this case. I think they did it for a reason when they were writing the problem. Jupiter and Saturn they're almost in what's called conjunction, the closest point they get during the year. The right ascensions are virtually the same. The declinations are only off by a little bit. So if you were looking up into the sky, Jupiter and Saturn would be very close to each other. So right away, if you look at choice B for this question, where it offers Jupiter, Saturn, and I forget the other one, Polaris, that's out because these things are going to be right on top of each other. But let's plot them onto the star finder, shall we? All right, so what we want to do is spin the 0 point over to the right ascension. So I think, let's see, for Jupiter it was 190.02. So I have it set to just a hair over 190. And then the declination is northerly or southerly, right? So it's southerly, so it's going to be below the 0. We're in the northern. If it's opposite, you go on this way. And if it's the same, you go on this way. So it was a declination of like 2 degrees, 43. We just do our best. There's Jupiter. Okay, so I'll zoom in for a second. I just plotted Jupiter at the correct declination and the right ascension. And then if we spin this to right ascension 189. There we can plot that with a right ascension of 189 and a declination of a little less than 2. There's going to be Saturn. So what we've done now is we've got this plate and we put the planets where they go. So the last step is to take our standard plate for 25 degrees north, spin it hour angle of Aries, which was like 194, and then take a look at the options that we have. All right, so the 4 choices, and anytime you have one of these kind of problems, you really gotta, unfortunately, go through all of the answers. So we'll do that. Choice A is correct. I told you that, so I guess I gave it away. But let's see why the other ones are incorrect. All right, so choice B, Jupiter, Saturn, and Polaris. Well, Jupiter and Saturn are right here. They're right on top of each other. So that's not going to be a good object to use. Polaris is right here, and it's also like directly opposite of Polaris. So this is doubly bad. So choice B is out. How about choice C, Saturn, Polaris, and Zubenelgenubi, which is the best name for a star, by all means. Here's Saturn. That's a good place. It's 60 degrees high. Here's Zubenelgenubi. It's a little close to Saturn, like let's see, 10, 20, 30, 40. It's about 40 degrees away, so that's not terrible. So we're good so far. But here is Polaris over the North Pole, opposite of Saturn. So they would not yield a good fix. They would just give 2 lines right on top of each other. So choice C is out. All right, how about choice D? We got Jupiter, which is there. Jupiter's a good object. We have Spica, which is right here. Spica itself is a good object. However, it's very, very close to Jupiter, so that's not going to be good. And then Denebola, I think, was the other one. I'm forgetting where that is right now. Regulus. Denebola right there. So Denebola is actually very high in the sky. It's like 70 degrees high. So choice D is out as well. So we're left with choice A. Saturn, which is perfect. Regulus, which is also perfect. And then Antares, which, let's try and find it. Get where that is. Antares here. Antares is actually a little bit low, but given the other 3 choices, that's going to be the one we want to go. All right, so that's a Starfinder problem with planets, kind of a rare thing, but they are on the Coast Guard problems. So that's the second of our problems for tonight. The third problem we're going to work, this next problem that we're going to work, is an amplitude of the moon. So if you remember kind of the basics of amplitude problems, we said that imagine yourself sitting on a beach and you're looking out at the water and you're looking at sunset. So there's due west. On the equinox, the sun is going to set right west like that. And then if you're in the northern hemisphere, in the summer, the sun is going to track its way over to here till it reaches the solstice. Then it's going to track its way back, and in the winter, it's going to head towards the south. Not all the way to the south, just the southwest. So this distance is called amplitude, and you can calculate it for any day of the year based on 2 things. 1, your latitude, and 2, the declination of the body. So we did sun problems previously, but you can do it for any body, right? Planets, stars, the moon as well. So what makes the moon different? Not a lot in the first part, but what does make the moon unique in the problem that we selected is the time at which you have to observe these things. So if you want to take an amplitude, you should do it when the sun is 2/3 of its own diameter above the visible horizon, right? If this is the visible horizon, that makes the sun on the celestial horizon. And that's when all the calculations are based on, right? So for the sun, we want to be 2/3 of its own diameter above the visible horizon. For a star, we want to be about 1 sun diameter above the visible horizon, and that makes us on the celestial horizon when all the calculations are based on. For the moon, take a guess. Where do you think it's going to be, right? It's kind of weird. It's actually in this position. When you first see the moon pop up over the horizon, it's on the celestial horizon. That's because the moon is so darn close to the Earth that it makes that difference. So if you want to take an amplitude, these are the times to do it. Stars and planets, the sun, and the moon in these different locations. If you miss that point, you can fix it with a correction. And so in our problem, it says that the moon looks like that. So we have to apply a correction for it. It's a table 28 correction, right? And you can do the same thing for stars and planets if you happen to miss it. The reason why you have to do this is objects don't sink directly down to the horizon, depending on your latitude, of course, right? If you were to track the moon rising, you know, it's going to start out here. That's the time to take it. And then it's going to, you know, rise up in some orientation depending on your latitude and depending on the declination of the body. So if we miss this point, we can't take a measurement to it, or else we're going to be wrong. The whole point of doing an amplitude is to take a measurement so you can get a true bearing that you can then compare to your compass to get compass error. All right. So for the moon, for this problem, it's on the center is on the visible horizon, which means we have to make a correction for it. So the salient points in this problem, and resources for this, we're going to need Bowditch for this. Oh, in the Nautical Almanac. Okay, so we're on the 16th of April, and it's 14:30 zone time. And our position is 34 degrees 03.8 minutes north and 61 degrees 02.5 minutes west. So kind of like in the last problem, what time zone are we actually in is important. 61 degrees divided by 15. We're in a zone descriptor of +4. Some people call that -4, and so if you're like in the civilian world, the minuses and the pluses are often switched for the maritime world. But in essence, what this is saying is add 4 hours to it, and you're going to get to Greenwich time. So our Greenwich time is 1830 GMT. That's the time of the site. So we don't actually need our longitude anymore, but we can fix this a little bit. Well, actually, we don't even need to. Normally, we would put this into like decimal notation. We can do it just for the heck of it, but it's going to be necessary for this problem. 34.06 degrees. So if you wanted to do a trig calculation, you can get an amplitude that way if you want. We're going to use the tables though, so it's not that critical. Okay, so we saw the moon rising. It doesn't say rising, but it says we observed it at 0.95. What was it? 0.95.2 degrees per steering compass is what we looked at it. So the moon is rising in this case because we're looking out to the east. So we want to calculate the true amplitude so that we can do something like this. Our compass course is 0.95.2, and our variation was listed in the problem as 12 degrees west. If we can figure out what the moon should have been true, we can solve for the deviation in the magnetic compass. All right, so that's our goal, is to get this true value and go from there. Okay, so where can we go for this? Well, it's going to be table 27 in Bowditch. Latitude, which we got, and the declination, which we can get. So let's pop over to the Nautical Almanac and get the declination for this day, 16th of April. Oh, press the wrong button, I guess. Sorry. All right, so here is the Nautical Almanac. Here's the moon. We got the 16th of April. So we're going to look for the declination of the moon on the 16th of April at 1830 GMT. So at 1800, it looks to be north 4 degrees, 17.0. And then an hour later, it's 4 degrees, 06.5. And we're exactly halfway between because we're at 1830. This little D number here represents the hourly change in declination from 1 hour to the next. So if we just cut that number in half, we got what we need, and we're good as gold, right, for our correction. So we'll take the declination, change colors here, of 4 degrees, 17.0. And it was northerly declination. And it was changing at that rate. We'll subtract that. We got our declination. Bam. So we got our declination. We got our latitude. So we can use Bowditch now to get the amplitude. We're done with the Nautical Almanac for the semester. What a great feeling, right? So Bowditch has these tables in them, and you can memorize them or just look up in the front. Amplitudes, altitude correction there. Amplitudes table 27. Right. The other thing actually I want to point out is there's a nice description in the front right before. This book is available to you on the Coast Guard exam, so you can teach yourself the thing during the problem if you forget. So don't stress too much about it. So we need the latitude and we need the declination. We said our declination was 4 degrees and a little bit of change, and our latitude was 34 degrees and a little bit of change. So let's see how accurate we can get here. 4.8 stretching to 4.9 for latitude, and then 4.8 stretching to 5.4 for the declination. So this is one that we can mentally interpolate if we want, and if you follow along, you can see that it's going to come up to 5 degrees. 5 degrees, because we're a little more than 4 degrees. You could do the ratios if you want, but mental interpolation is going to be sufficient for that one for sure. So that's good. Our amplitude is 5 degrees. What does that mean? Is that the value that goes in here? No. What they're saying is you're looking to the east and you're going 5 degrees to the north of it because the declination is north, otherwise known as 085 degrees true. So normally that's what we would put in here, 085 degrees true, so we can solve the problem. However, we missed the correct time. So we have to make a little correction to it, a table 28 correction, right? It's not that significant, but it is necessary, especially for calculating compass error for sure. Let's take a look at a couple things regarding table 28, which is the correction of amplitude on the visible horizon. It also needs declination and latitude, right? And so let's see what ours comes out to be. Correction looks to be 0.5. 0.5. So keep that number in mind. Sorry, you can't see that exactly. But let's read the instructions for this table first. Table 28, correction of amplitude as observed on the visible horizon. For the moon, apply half the correction toward the elevated pole. Okay, crazy. Use of this table is explained in section 720. Let's go look at that as well, because this is I find it an interesting topic, and I think a lot of people do these problems wrong, I would say. Just saying. So here's the amplitudes chapter, and like I say, this is available on the test, so you can read it to yourself if you want. But if you kind of boogie on through it, going to say, if the body is observed when its center is observed value, the observed value should be corrected. So we don't necessarily want to correct this. We want to correct this. Normally, that's what we want to do. However, let's take another look. If preferred, the correction can be applied with the reversed sign to the value taken from table 27, and then compared with the uncorrected observed value. So it's a little bit weird. We said our value was 0.5 out of that, so that's good. But it's really important to read these, because if you're tweaking this by half a degree the wrong way, now you're going to be 1 whole degree off. So it's saying that you should correct this, or if you want, you can apply it in the opposite direction to this one here. So what that boils down to, you can press the I believe button if you want, but we need to apply half that correction, which is 0.25 or 0.3, to the nearest rounding, and we need to add it. So we get 085.3 degrees true. So that little hanger-on might make the difference between getting the problem correct and getting the problem incorrect. So all that's left now is a standard compass correction. True vampires make dull companions at wakes. So we take 085.3 plus 12, and we get 97.3. Subtract 95.2. And we get our final answer, 2.1 east. All right, so that's an illustration of kind of how this whole thing works for the amplitudes when they're in the wrong position in any case, right? So you can observe the sun, the planet, and the stars at the correct time when they're on the celestial horizon, or you can make a correction to them if you kind of miss that time. All right. So that wraps up that problem. So I'll clean up the board, and that's kind of the last problem that I wanted to work tonight. So I just wanted to thank you for kind of hanging on over these weeks as we went through the navigation problems in the evenings. I had a lot of fun doing it, experimenting with live streaming. I learned a lot as well, so that's good. And I wish you the best studies. If you do have a chance to check out that course, I would really appreciate it. For those that are watching right now, I've got a limited number of coupons that say SEA. You can get 90% off it. I'm not going to write it down anywhere, only for you if you're watching. SEA is the coupon code for that one. And there's only a couple, so it's going to disappear fairly soon. All right, so I'll be back in the fall with some different stuff. And in the meantime, I'm going to go back to making videos. So I'm thinking about doing some videos about sextant corrections and that kind of stuff. But if you have any ideas, send them my way. And likewise, if you are studying for your exam, feel free to send me an email at chris@practicalnavigator.org, and I can point you to some resources, study resources for getting through your exam. All right, best of luck to you. Happy navigating, and take care.